1 to 3 points which are permanently at rest, and such points are called nodal points, and we will represent them by N. This is a nodal point, this is a nodal point, and this is a nodal point. Points where the string segments have maximum displacements. If you notice, this is a point where the string segments will have maximum displacements. Now such points are called antinodes. We will represent that by the uppercase A. This is an antinode, this is an antinode. Now, you can see this mode, the process of maximum and minimum displacements appearing and disappearing is called the formation of stationary waves. So the process of forming stationary waves on a stretched string is due to the formation of maximum and minimum displacements appearing and disappearing due to the interference of the advancing and the reflected wave. Alright? Okay. Now, the wavelength of a stationary wave. You know, in the last lesson we talked about the wavelength. Now, you know that wavelength of a wave contains a full crest and a full trough. You see that? A full crest and a full trough. So, in the case of a stationary wave, you know, a stationary wave produces segments. You notice that this is a segment. The distance between two consecutive nodes can be considered to be a segment. So how many segments are here now? 2 segments. Now the wavelength of a stationary wave is the length of 2 segments. The distance between 2 alternate nodes, not the distance between 2 nearest nodes. The distance between 2 alternate nodes is the wavelength of a stationary wave. Alright. Now, therefore, the distance between 2 adjacent nodes will be half of a wavelength. The distance between 2 adjacent antinodes will also be half of a wavelength. So, wavelength is the length of 2 full loops. A segment is a loop. Is that right? It's better to call it a segment rather than a loop. The number of nodes and antinodes on the string depends on the frequency of vibration of the string. Now you remember I told you that by the time the vibrator completes one vibration, if the wave goes and comes back, then the string will vibrate in one segment. But suppose by the time the energy goes and comes back, if the vibrator completes 2 vibrations, then the string will vibrate in 2 segments. Now, by the time the energy goes and comes back, if the vibrator does 3 vibrations, then the string will vibrate in 3 segments. That means the number of segments that are produced in a stationary wave depends on the frequency of vibration of the vibrator. Well, I think I'm going to demonstrate that to you. I will show that to you in a demonstration a little later. Alright, let's see if I can demonstrate that to you. I have now a string stretched between the mechanical vibrator and the fixed end. You can see the string vibrating. The mechanical vibrator vibrates up and down. Now, if I can adjust the frequency of the vibrator such that by the time it completes one vibration, the energy goes to this end and comes back, then this string will vibrate in one loop. Let me see if I can do that for you. I'm going to increase the frequency and, well, Do you see the string vibrating in one loop now? There is one segment. That means you have, look at the antinode. Where I'm pointing is the antinode. This is the node and this is the node. Now at this time, when the vibrator completes one complete vibration, the energy goes to the end and comes back. The new energy of the vibration now get reinforced with the reflected, and you can see there is constructive interference here. Now I'm going to double the frequency of the mechanical vibrator, see what happens. Alright, that is our one loop. Now I'm increasing the frequency. You notice that the segments have disappeared. Alright, let's increase the frequency. What is happening now? The string is beginning to vibrate now in two segments. Now notice this beautiful two-segment vibration. Now that means by the time the vibrator completes two vibrations, the energy goes and comes. You can see there is a node here, an antinode here, a node here, an antinode here. Okay, if I make the frequency of this 3 times the original frequency, what will happen? I'm going to make the frequency 3 times and see what happens now. Alright, now the frequency of the mechanical vibrator now is 3 times the original frequency, and you have 3 full segments. You can see a node, a node, a node, a node, an antinode. Alright, I touched it. Antinode, antinode, antinode. Now, what is the wavelength of this wave? If you want to measure the wavelength, you need to measure it from one node to the alternate, to here. That will be a wavelength. The length of one segment will be half of a wavelength. Okay, I'm going to now increase the frequency to 4 times the original value. Alright, see what happens now. There you are. The string is now vibrating in 4 segments. Isn't that beautiful? So how many nodes are there? There is 1, 2, 3, 4, 5 nodes. How many antinodes are there? There's 1, 2, 3, 4 antinodes. Now these are stationary waves. I hope you enjoy watching these stationary waves. Alright? Now watch this computer animation of a stationary wave. Advancing wave gets reflected. The advancing wave and the reflected wave now interfere, producing the stationary wave. Now this is how stationary waves are formed. This is the case of one segment vibration. In other words, the frequency of the vibrating object is such that by the time the energy advances and returns, it completes one vibration. And now, if you double the frequency, you will get 2 segments vibration. There you have the 2 segments vibration. You have 3 segments vibration, and so on. Well, you have now got a clear picture of stationary waves. Now, what is the simplest mode of vibration of a string that is stretched between 2 points? The simplest mode of vibration is that you have nodes at the fixed end and an antinode at the middle. Is that right? It will look like this. This is the simplest mode of vibration, with a node here, an antinode here, and a node there. And what is the length of the string in relation to the wavelength at that time? Can you tell me? This is the complete length of the string. The complete length of the string now contains how many wavelengths? the distance between two adjacent nodes is half of a wavelength. Is that right? Now, the frequency of the string vibrating like this is called the fundamental frequency of the string. So, when the string vibrates in one segment, the frequency of vibration is the fundamental frequency. Okay? For the fundamental mode, the length of the string contains half a wavelength. That means this length from here to here will be half of a wavelength. We will say the length L of the string equal to lambda by 2, or the wavelength of that stationary wave will be 2 times the length of the string. So the length of the string now contains half a wavelength, or the wavelength will be 2 times the length of the string. Now, what is therefore the frequency of the fundamental mode? Now remember that wave equation. What is our wave equation? Do you remember? The equation that connects the wave speed, frequency and wavelength. V equal to F lambda. Therefore, F equal to V over lambda. Now, I'm going to call the frequency of the fundamental mode as F1. So, F1 equal to V over lambda, and for the fundamental mode, lambda equal to 2L, and therefore, this is the frequency of the fundamental mode of vibration. F1 equal to V over 2L. Alright, don't forget this. This is the frequency of the fundamental mode of vibration. What is the next higher mode of vibration? When you double the frequency, the string begins to vibrate in 2 segments. And so, the next higher mode of vibration is this. The string vibrates in 2 segments. That means there is a node there, a node here, and a node at the other end. There are 3 nodes, and how many antinodes? 2 antinodes. This is the second mode of vibration. The frequency of this is twice the fundamental and is called the second harmonic. The string is now vibrating at twice the fundamental frequency, and twice the fundamental frequency is called the second harmonic. For the second harmonic, what is the relation between the length of the string and the wavelength? You can now see the full length of the string contains 2 full segments. That means it contains a full wavelength. Is that right? Yes. The distance between 2 alternate nodes is now a wavelength. So the length of the string now contains a full wavelength. So the wavelength of this mode is lambda equal to L. Therefore, you can see, therefore, what is the frequency of the second harmonic? Well, F equal to V over lambda, is that right? I'm going to call the frequency of the second harmonic as F2 equal to V over lambda. And what is lambda equal to for the second harmonic? Lambda equal to L. So that will be V over L. And I can write this as 2 times V over 2L. Why did I write like this? Because V over 2L, if you remember, is the frequency of the fundamental. So the frequency of the second harmonic is 2 times the frequency of the fundamental. It is 2 times F1. The second harmonic is twice the fundamental. Now what is the next higher mode? In the next higher mode, the string will vibrate in 3 segments. Now look at these segments. This is the third mode of vibration. You have a node